Hi, maths students. It's Mr. Hajgassam here, and today we're going to be learning about limits of accuracy and more specifically bounds. So here's a question for you. So if a fridge is 600 millimeters wide to the nearest 10 millimeter, would it fit into a gap that is exactly 600 millimeters wide? So you can pause the video and have a think about this. Now, let's say then, what does this actually mean? So the fridge is 600 millimeters wide to the nearest 10 millimeters. So what that could mean is that the fridge may be, let's say, 590, well, if it was 594 actually, to the nearest 10 millimeters, this would round to 590 millimeters. So it can't be 594 millimeters, and I'll put the units here. What if it was, however, 595 millimeters? Well, in this case, 595 to the nearest 10 would be 600 millimeters. What if it was then, let's say, 596 millimeters? Again, that would round to 600. And if we had, say, 597, that would also round to 600 millimeters. And if we had, say, 599.9 millimeters, that again to the nearest 10 would be 600 millimeters. If we even had, say, 604 millimeters, again to the nearest 10, that's going to be 600 millimeters. And if we had 604.9999 recurring, that again would round to the nearest 10 to 600 millimeters. So the width of this fridge that we want to put into our kitchen or wherever we want to put it in, so long as it fits into this gap here, the width can actually vary because we've estimated it to be, or rounded it to be, at 600 millimeters to the nearest 10 millimeter. So given the range of answers we have, what we can start to say is that we have a lower bound. So the lowest possible value that would round to 600 millimeters is going to be 595. So this is our lower bound. So this could potentially be the width of our fridge. So our lower bound is 595. And then what is our upper bound then? Well, we said the fridge could be 604.999. It can't, however, be 605 millimeters. And that's because 605 to the nearest 10 would round to 610 millimeters. However, the upper bound we would write as 605. So this over here, 605 would be our upper bound. And if we think about the definitions, the lower bound is the smallest value that would round up to the estimated value. So this is the smallest value that would round up to 600 millimeters. The upper bound is the smallest value that would round up to the next estimated value. So 605 would round up to 610. So in essence, the width of the fridge is greater than or equal to 595, but less than 605. So all values from 595 all the way up to, but not including 605, could be the width of our fridge. And this is what we call an error interval. And our error interval is made up of our lower bound and our upper bound. All right, so let's try another example then. So let's think about someone quite famous who you might know. So Cristiano Ronaldo. Cristiano Ronaldo is 187 centimeters to the nearest centimeter. So what could be the range of his height, or what could be the error interval? Well, let's think about it. To the nearest centimeter. So if I just draw a number line here, that's another way of doing these problems. So Ronaldo to the nearest centimeter is 187 centimeters. The next centimeter up is 188 centimeters. And the next centimeter down is 186 centimeters. So the error interval would lie in between 186 to 187. So that would give us our lower bound, which is 186.5. And our upper bound would be 187.5, because all values within this range would round to 187. So for instance, if we had 186.5, that would round to the nearest centimeter to 187. If we had, say, 186.78, again, to the nearest centimeter, that would be 187. If we had, say, 187.4, this to the nearest centimeter would again round to 187. And if we had 187.49 recurring, that would again round to 187 to the nearest centimeter. So our lower bound and our upper bound are these two numbers here. And if we were to write the error interval, we could say the height of Ronaldo is greater than or equal to 186.5, but less than 187.5. So again, we have our lower bound and we have our upper bound here. And this is how we write our error interval. So any value within this range would round to 187 centimeters. Okay, so let's try some more difficult examples then. So here's a question for you. It says, the number x rounded to one decimal place is 5.7. Write down the error interval for x. So again, we can draw a number line. And if I just move this over here, and on our number line, I can write the number 5.7. Now, one decimal place down would be 5.6. One decimal place up would be 5.8. And our error interval would be the numbers between 5.6 and 5.7, where that's going to be 5.65. And this is going to be 5.75. Sorry, I know it doesn't look perfectly symmetrical. So here it is. All numbers within this error interval will round to 5.7. So our error interval would be our lower bound, which is 5.65, is less than or equal to x, and x is less than 5.75. And once again, this is how we would write the error interval. Let's try a different example. So the number y rounded to two decimal places is 7.36. So once again, I can use my my number line. So I've got my number, which is 7.36. Two decimal places down would be 7.35, and two decimal places up would be 7.37. So once again, to find my lower and upper bound, I need this midpoint here. So this is going to be 7.355, and this is going to be 7.365. So the reason why I've done it like this is because it says the number has been rounded to two decimal places, whereas in the first example, the number was rounded to one decimal place. So you need to look at the degree of accuracy, and that's how you can determine your upper and lower bound. All right, so let's write our error interval here. So our error interval will be, so 7.355 is less than or equal to y, and y is less than 7.365. And the last example, so this one's a little bit different because the degree of accuracy is in significant figures. So it says the number z rounded to two significant figures. Now, what you need to do is count where the second significant figure is. So the second significant figure would be the 8, and the 8 is in the hundreds column. So what this essentially means is the number has been rounded to the nearest 100. So in this example, two significant figures just means to the nearest 100. If, say, for instance, the question said the number z has been rounded to one significant figure, well, the first significant figure is in the thousands, so the number would have been rounded to the nearest 1,000. So just be mindful of the wording, especially where they give you significant figures. All right, so write down the error interval for Z. So once again, I'm going to draw my number line. And I've got my number, 5,800. So 100 up would be 5,900. 100 down would be 5,700. And now I can find my error interval, or my lower and upper bound, to then write my error interval. My lower bound is going to be 5,750, because anything between 5,750 and 5,800 would round to 5,800, and my upper bound would be 5,850. So once again, this is our error interval, and we can write that as 5,750 is less than or equal to Z. Z is less than 5,850. So we have our lower bound and upper bound and our error interval. All right, so let's try some more difficult questions. So what do we have over here? So this one's a little bit tricky because we're dealing with different units. So it says Elliot weighs 56.2 kilograms. The mass M is to the nearest 100 gram. Write down the error interval. So once again, we need to work out the bounds here. Now notice we have a slight problem, and that's because we are working in kg and grams. So what we need to do is convert either the kilograms to grams or the grams to kilograms. Now I would rather convert the kilograms into grams, but you could do it the other way around. It doesn't really matter. And to go from kilograms to grams, we need to multiply this number by 1,000. So what we get is 56.2 kg is equal to 56,200 grams. So we simply multiplied this number by 1,000 to convert it into grams. So now this number to the nearest 100, now we can work out the error intervals. So I'm going to draw my number line. So I've got 56,200. The next 100 up, because we're working to the nearest 100 grams, so the next 100 up is going to be 56,300, and the next 100 down is going to be 56,100. And again, our lower bound is therefore going to be 56,150, because this number to the nearest 100 would round to 56,200, and our upper bound would be 56,250. Anything just below 56,250 would still round to 56,200. And our error interval would therefore be 56,150 grams is less than or equal to the mass of Elliot, and that mass is also less than 56,250. And because we've written it in grams and the question doesn't specify whether to give our answers in grams or kilograms, we can leave our answer like this. But if you wanted to work in terms of kilograms, you can simply divide both numbers by 1,000. And what we get is going to be 56.150 kg. And then we would get 56.250 kg. So both answers would be perfectly fine if you wanted to give your answers in terms of grams or kilograms. But the key thing here is to convert your units into the same unit before you start the problem. So we can either work in terms of kgs or we can work in terms of grams. It doesn't really matter which way around you do it. All right, let's try another example. So what do we have over here? All right, so this one's a bit of a tricky question because it says pinboard is measured as being 0.8 meters wide and 1.23 meters long to the nearest centimeter. So again, we have different units. Calculate the minimum and maximum possible values for the area of the pinboard. So if the pinboard is a rectangular pinboard, what we'll have for the area would be the width times the length. So we want the maximum possible width and the smallest possible width. So once again, we need to work out the bounds for our width and length. But before I do that, I'm going to convert these into centimeters. So I'm working in 1 unit. So 0.89 meters is 89 centimeters. And 1.23 meters is going to be 123 centimeters. So we're just multiplying by 100. All right, so now let's work out the error interval for the width. And then we can work out the error interval for the length. So the error interval for the width is going to be, again, you can draw your number line, but because it's to the nearest centimeter, so that's going to be 80. So it's going to be 88.5 and 89.5 would be the upper bound. So these are our bounds, our lower bound and our upper bound. The length, so what we have, again, it's to the nearest centimeter. So the lower bound is going to be 122.5. And the upper bound will be 123.5. Now, right now, we're working in terms of centimeters. We could then rewrite the bounds in meters as well. So if I was to write them in meters, so I will use a different color pen. So I would have to divide by 100. So what we'll get is 0.885 meters and then 0.895 meters over here. And for the length, I will get 1.225 meters and 1.235 meters. So you can do the calculations whichever way you prefer, whether you want to do it in centimeters or in meters, it doesn't really matter. But we want the maximum area then. So the maximum area, the largest possible area would be the largest length times the largest width. So the maximum area, so we can say max area would be the upper bound of the width times the upper bound of the length. So what we would get is 0.895 times 1.235. And the max and the minimum area would be the lowest possible width multiplied by the lowest possible length. So that's going to be 0.885 times 1.225. And if you type this into your calculators, you will get your answer. So I'm just going to quickly type this into my calculator. And that's going to be 0.895 times 1.235. And that will give me 1.105 325. And if I just move this here. And then my minimum area, that's going to be 0.885 times 1.225. And that will give me 1.084125. Now the question might have said, calculate the minimum and maximum area, give your answer to say 2 significant figures or to 2 decimal places. So again, depending on what the question is asking you, give your answer to that degree of accuracy. And one thing I forgot is meters squared. because we used meters in both examples. All right, so this one, again, you didn't have to do anything out of the ordinary. You just have to work out the upper and lower bounds, and then think about it. The maximum area would require the highest possible length and the highest possible width, and the minimum area would require the lowest possible length and the lowest possible width. One last example. So these ones can be a little bit tricky because we're dealing with fractions. So it says S is 4.15 correct to 2 decimal places. T is 2.516 correct to 3 decimal places. Work out the upper bound for V. So we want the highest possible value of V. Now, that doesn't necessarily mean we would have to use the upper bound for S and the upper bound for T, because what we want is the largest possible value for V. And we can think about this in terms of money. So let's say if we had, each pound sign is, say, £100. Let's say if we had £400 and we were to split it between 2 people, what we would get is each person would get £200. If, however, we had, say, again, £400 and we were to split it between 4 people, each person would now get £100. So whilst the numerator remains constant, if the denominator gets bigger, the answer we get, the result we get, is actually going to get smaller and smaller. So what we want in an ideal situation to get the highest possible result, we want the highest, largest amount of money divided between the smallest number of people. So in this case, it would be V, or upper V would be the upper bound of S divided by the lower bound of T. So the largest amount of money divided between the smallest number of people. And that's maybe the best way to remember these problems. Alternatively, maybe you could write out some fractions for yourself. So let's say 10 over 2 will give us 5, but 10 over 1 will give us 10. So, or better yet, 12 over 1 will give us 12. So as we increase the numerator and decrease the denominator, our answer is going to get bigger and bigger and bigger. So in situations like this, we want the highest value of S and the lowest value of T. So what we need to work out is the upper bound of S. So the upper bound for S will be, so upper bound for S, so it's 2 decimal places. So that's going to be upper S. So upper bound for S, or maybe I should write SU. That'd be better. So the upper bound for S is going to be 4.155 to 2 decimal places. And the lower bound for T, so T lower, that's going to be 2.5155 to 3 decimal places. And now that I have the correct values, I just need to substitute that into my formula or equation. So let's do that. So what we get is V upper is going to be equal to 4.155 divided by 2.5155. And I'm just going to double check to see if I've got that right. And yes, I have. That is correct. And then once we type that into our calculator, we will get our answer. So that's going to be 4.155 divided by 2.5155. And that gives us 1.651759 and so on. But the question says round your answer to 3 decimal places. So that's going to be 1.65, and that 1 is going to round up because of the 7. So 1.652 is our answer. All right, so I hope you've enjoyed this lesson. So key things to work out is if you want to work out the upper and lower bound of a number, you can draw a number line, and you can go up in different degrees of accuracy to work out your lower bound and your upper bound. And then you can write your error intervals, and then you can apply that to a range of problems as we've done here and in the example where we had to work out different areas. I hope that's helped, and have a very good day. Bye.